I'd like to begin by thanking all the organizers for putting up this nice event, and of course for kindly inviting me to speak. So yeah, today I will return back to this interesting phenomenon of superdiffusion that we already heard about in this conference a couple of times actually. But today I want to focus on models which possess a larger amount of symmetry, so symmetries of higher rank, and I will cover mostly quantum models or quantum spin chains. But in the end, if there will be time, I will also tell you a little bit about classical integrable system with higher symmetries. Well, we know quite well, right, that in one dimension there is a very rich variety of non-equilibrium phenomena, and in particular we heard already that integrable systems are paradigmatic examples of models that display unorthodox phenomena. So this can be exactly integrable models, but we also heard that even if we mildly break integrability, there can still be some anomalous features left. And so, yeah, one of the prime examples of that is the recently discovered superdiffusive spin transport in the isotropic Heisenberg chain, which is now believed to belong to the KPZ universality class. So since we've already heard about this topic, as I said, so in particular, on Tuesday, Joel told us about the broader picture and gave some historical perspective, and then explained this recent Newton scattering experiments, which were able to confirm that this superuniversal superdiffusive transport takes place in certain spin chain like compounds. And then also Joel posted then so yeah, so Romain told us about the theoretical framework of generalized hydrodynamics and how within this framework this phenomenon can be explained. In particular, that if we are at finite temperature and at half filling, then there will be essentially perfect screening of spin degrees of freedom due to mutual interactions, which will completely the Drude weight and the diffusive spreading, which in principle is what one would expect on a sub-ballistic scale, as then blows up due to the contributions coming from giant quasi-particles. And he told us that this can be viewed as at the classical level as solitons degrees of freedom, and then discuss various aspects of breaking. So in this talk, I cannot afford to again repeat all these things, so I'll permit myself to skip the introduction and these historical developments, and focus really mainly on the role of symmetry. So so what precise role does the symmetry algebra play here? And the idea is to investigate transport properties not only in this basic example of the Heisenberg SU2 symmetric spin chain, but also in other quantum spin chains that possess a larger amount of symmetry, by which I mean they are globally symmetric under Lie groups of higher rank. So this talk is divided into two parts. So the first is the summary of a recent paper which was published in PRX, which is a joint work with Jacopo De Nardis, Alanko Balakrishnan, Romain Vasseur, and Brain Aware. I'll spend most of the time on this part, and then if time permits at the end, I will discuss our side-post paper with Giga Krajnik and Tomasz Persen on the classical integrable system with higher rank symmetries. So let's maybe first discuss what should one a priori expect if one puts even more symmetry into an integrable model. So here I listed a few perhaps most suggestive options in no particular order. So one is, well, let's say optimistic expectation would be that the phenomenon is much more universal, and that indeed all integrable models that enjoy non-abelian symmetry will display the same type of superdiffusion. So that's one possibility. And here I don't have a really precise mathematical definition of. I lost the screen. All right. I do not have a definition of what do I mean by all, but I hope this is fine. If you're a physicist, I hope this is okay. The other option would be that if one considers other classes of symmetries, so by classes I mean unitary symmetries, orthogonal symmetries, symplectic symmetries, or goes to higher rank symmetries that one finds different anomalous diffusion laws characterized by different dynamical exponents. And the third option is that it can be even more rich, and that even the type of local degrees of freedom that one chooses may play a role. So, I guess the intuition behind expecting some possibly some richer spectrum of dynamical exponents could come from this work on the Fibonacci universality, which was found in non-integrable systems that possess a larger number of conservation laws. This is the prediction of the nonlinear fluctuating hydrodynamics. So the idea could be that if we have more symmetry, this means there will be a larger number of the Noether charges due to the symmetry in the system, and these charges might couple in some intricate way, and ultimately result in some fractional dynamic exponents which are different from the z equal 3/2, which is what happens in the SU2 chain. So our work was not really. So there has been a number of work before our work which gave some insight into what might happen. So first of all, we know we have an analytic proof that in a large variety of integrable quantum chains, the diffusion constants are divergent. So most prominently, the Fermi-Haber model or the supersymmetric TJ model. So these are the models of strong interacting electrons. So we know there will be some type of diffusion. But then is also independent numerical evidence which points toward option 1. So the paper by Dupont and Moore, which I believe they simulated with the MRG the SO5 symmetric spin chain, and they found also that there is the Z equal 3/2 dynamical exponent there. So then is the work I will be talking about at the end, much % on the classical systems with non-abelian symmetry, which also show very clearly the same exponent, and the work by Fava et al., which then confirms the same exponent in the Fermi-Haber model. Okay, so this is a good indication. But then there were some earlier works, in particular by Žnidarić from 2013, where he simulated an integrable spin ladder with SU4 symmetry, which shows that the exponent might be closer to 5/3 instead of 3/2. This is, of course, just a numerical fit on the data. So the question is, can we find can we get some theoretical arguments to deduce these dynamical exponents for different types of symmetry? So that's the main goal. Now, to address this question in a systematic fashion, it will be necessary to.
Sorry, Enej, the sound. Yeah, we can't hear.
Sir, can you directly use the laptop speaker itself?
Yeah, I'm using the laptop speaker, but there is some auto-adjusting, which I'm not sure how to switch off immediately. So now you hear me well?
Yeah, now we can hear you.
Okay, sorry for that. So yeah, so I would like to give you a little bit of more formal treatment of this before I summarize the main result. It's not that I want to torture too much with the beta ansatz things, but I believe there is a really elegant formalism behind it, which nicely shows how symmetry algebra dictates the structure of the quasi-particle spectrum, and then how this this information enters into the hydrodynamic data that ultimately decides which dynamical exponent you will find in the system. So I wanna briefly sketch the main steps of the formalism that we use to establish our result. So as Joel already said on Tuesday, you can think of quantum integrability in the Yang-Baxter sense as a completely factorizable elastic scattering of quasi-particles. So this works in the following way. You know from school that if you had just free non-interacting particles and then you subject them you put them in a finite volume, right? The periodic boundary condition will quantize the allowed values of quasi-momenta that these particles have. And now what is remarkable is that there exist systems where, despite interactions among the quasi-particles, the same principle holds. So the quasi-momenta are well-defined quantum numbers, but the quantization condition changes a little bit due to interactions. And what happens is that when one quasi-particle scatters of other quasi-particles, it just picks up some U1 phase factor upon collisions. And these are the celebrated beta equations, which I wrote here. So then, if you have more particles in the system, so they were all scattered among each other, but because individual quasi-momenta are preserved at each collision, it means that the total set of quasi-momenta will be the same at the end. So the outgoing state will have the same quasi-momenta, just permuted in the different order. So for this to happen, one has to ensure that the way that the order in which these particles scatter shouldn't matter. And for this, it's enough to require that there is a consistent, so that in which three particles can scatter yield the same result. And this is essentially what the Yang-Baxter equation encapsulates. So here I written that it's written at the bottom. So in practice, then, to find different types of quantum integrable models, one just starts with this algebraic equation and then looks for different solutions of it. And this then eventually allows you to find infinite sets of mutually commuting hundred. So now, as I said in this talk, I'm interested in particular in non-abelian symmetry. And so the question is, how does this picture get modified? And so one problem with this immediately is that when you have a larger amount of symmetry, it means that your quasi-particles will carry internal degrees of freedom, which can take many different values. And then what happens generically is that upon scattering, these internal degrees of freedom also get exchanged. So it means that upon scattering, there will not be just a U1 phase that you collect when a particle scatters with another particle, but there will be a matrix here. So this periodicity conditions of beta, now you would write it as a matrix equation. However, there is a way to overcome this difficulty. So again, to turn this equation into a simpler scalar equation at the expense of introducing auxiliary degrees of freedom. So you can think of these auxiliary degrees of freedom, if you think in terms of spin chain, for example, just as spin waves of different flavors that propagate on top of other spin waves. So there is some kind of a hierarchical structure. And then with this construction, the algebraic beta ansatz permits you to construct the entire set of eigenstates as you do it in second quantization. So you have a quasi-particle vacuum, and then there is a finite set of quasi-particle creation operators, which are here denoted by B, and there is one operator for each flavor that you have. Okay, and the number of flavors is what the rank of symmetry algebra dictates. So if you have a Lie algebra G, then its rank equals the number of different flavors that this quasi-particle will have. And then so then when you construct these states, they are not yet good eigenstates. You have to make sure that you sum them, that you create linear combination with appropriate amplitudes, and these F factors are then remarkably, they play a role of a wave function for a spin chain which has a symmetry of rank which is lower by 1. Okay, I will not go into detail how this works, but I just want to point out that there is some hierarchical structure how to generate wave functions in system with a larger amount of symmetry. But ultimately, these wave functions, what is important, they're uniquely characterized quantum numbers, which one can regard as quasi-particle rapidities. So there is index J, which labels different quasi-particles, and index A on the rapidity labels different colors or flavors. So A will always stand for this flavor index. So now, because quasi-particles are not free, the question is how to find this, these quantum numbers. And this can be done in a systematic way. And this procedure, which I'm going to outline, is called the nested beta ansatz. Nested is because of this hierarchical structure, and it works as follows. So, so we're going to pick some semi-simple Lie algebra G, which generates a compact Lie group big G from the list of the Lie algebras that were classified long time ago by Cartan. So then the idea is to promote this symmetry G to a quantum group. So a quantum group is a particular type of bi-algebra that mathematicians call Hopf algebra. So why this quantum group is important? Well, it turns out that quantum integrable models can be viewed as different representations of quantum groups. So you quantize this symmetry, and by generating different representations of this Hopf algebra that comes out of it, you will have different integrable systems. But we want in particular to retain invariance under the Lie group, and this only happens if this deformation parameter Q is set to 1. And in this case, this Hopf algebra is called, these Hopf algebras are called Yangians. Okay, this fact will become important a little bit later. So, so this is one thing. So we now have a symmetry of a quantum group that we produced out of a Lie algebra. And the second thing, we have to choose our degrees of freedom. So to do that, we choose one of the irreducible unitary representations of this algebra, which are characterized by the highest weight lambda. Okay, so, and then the task is to produce a quantum spin chain of length L that has this global symmetry over Lie group G, and degrees of freedom transforming this irreducible unitary representation, which is one of the rectangular Young tableaus, if you like. Okay, so now this is a fully general setting, and then you can ask what is the spectrum of eigenstates in such quantum spin chains, and what are the beta-like quantization conditions. And it turns out that they can be written in a very compact form. This is a result due to Reshetkin and Kirillov from the late 80s, where, okay, I'm not going to explain in full detail what this means, but the idea is that these representation labels govern the structure of the left-hand side of this equation, which you can think of for each flavor independently as the e to the IPL, where p is the quasi-momentum of a quasi-particle of that flavor. And the right-hand side, you can interpret as a product of scattering amplitudes. And it's always written as a ratio of two Q functions, and these Q functions are just polynomials that contain this quasi-particle rapidities. So that's the structure. So you can write it in one line. These are the equation that you have to solve. Now, what is nice is that each equation for a particular choice of Lie algebra in a representation can be depicted by a Kaji-Dinkin diagram. Here I give a couple of examples. So just to remind you, so there are in this Lie algebras, they contain 4 classical series, which are denoted by A, B, C, and D. And then there are some exceptional Lie algebras left, which I will not talk about. But so the rank of the algebra tells you like how many nodes are there in this Dinkin diagram, which corresponds to how many simple roots you have in your Lie algebra. And the numbers that you put inside the circles are then the so-called Dinkin labels, which tell you what is the weight, the highest weight of this representation that you choose. So the bottom line here is that this type of diagrams bijectically correspond to the structure of the nested Bethe-Ansatz equations. Okay, so this is now the finite volume spectrum so far that we have described. So now the task would be to solve these equations, and this is super difficult to find all the solution. But luckily, there are massive simplification if one goes to the thermodynamic limit, which is precisely what we are after. So then you go to large volume, you send L to infinity, and you consider eigenstates that have extensive amount of quasi-particles present of a different type of flavors. So this can be either single magnon excitations of different flavors, but then also they can these magnons of the same flavor can bind together and form bound states, which are known as the Bethe strings. So the precise structure of this excitation will not be important for what follows. So what is important that then in the thermodynamic setting, the thermodynamic ensembles or macro states, if you want, will be completely characterized by the densities of rapidities of quasi-particles of different type. Okay. So now the type of quasi-particle, so if rho of theta is the distribution of rapidities of a quasi-particle of type A, then the complete set of such function contains full information about the local physics of equilibrium states. Which brings us to the thermodynamic Bethe-Ansatz, because now we can operate with this macro state density as a variational objects, and then we can find the equations which will describe the thermal equilibrium. So let me just go briefly through it. So what happens is that you can find the total densities of a variable state. You can relate it to the densities of these quasi-particles in a given state. Where the essential information about the model enters through the scattering kernels, which are related to the scattering phases between different quasi-particle species. This equation can be also interpreted as the dressing of quasi-particle momenta, which is due to interactions with other particles. And then to describe equilibrium states, one can write an equilibrium partition sum as a functional integral, where these densities are now variational variables. So to each density, one associates a chemical potential or a fugacity, and then one has to use the appropriate entropy factor to account for the Fermi statistics of these quasi-particles. And then with the saddle point evaluation, one arrives at the celebrated TBA equations, which can be written again very compactly as this Fredholm type, a system of coupled Fredholm type equations. So again, this mu is the chemical potential of different quasi-particle species, and this is where the information about the state enters. And then the task is to compute the so-called Y functions by solving these equations. Y functions are by definition the ratios of the unoccupied modes with the occupied density of the occupied modes, and they provide the information about the Fermi-Dirac distributions of this mode. So N will be the Fermi occupation functions for each quasi-particle type A. Okay, so now I told you that the information about, so the information about the beta equations is completely dictated by the underlying symmetry algebra. So this is the kinematic data. So now one may ask if also states, so like, for example, the heap state is also fully governed by the Adler-like symmetry. Perhaps the intuitive answer would be no. Why should equilibrium states know anything about symmetry? But on the other hand, they are given by the exponents of the Hamiltonian, which knows about the symmetry, so that there has symmetry, something has to enter in some form. And so what is remarkable that, yeah, so let me first say one thing. So, so ultimately, these equations, the TBA equations can be again interpreted as the dressing equation for the quasi-particle. The dressing refers just to the effect of all other quasi-particles in a thermal state that have an effect on an individual quasi-particle. So formally, you can think of a mapping which takes the charge that the quasi-particle of type A with repeated theta carries, and then it dresses it, so it becomes modified. And this again corresponds to an integral equation of this type, where this Fredholm kernel again has the kinematic information from the scattering phase shift, and then dependence on the state enters through this Fermi occupation functions. And what is remarkable that this operator admits a very simple inverse. It can be inverted explicitly, and here I spelled out just to give you an idea. For the unitary groups, there are some universal type equations that one can find, and where the kernels are completely dictated by the Cartan matrices of the underlying symmetry. So it turns out that in general, so for instance, at finite temperature, these equations can only be solved on a computer numerically. So unfortunately, there is no closed form analytic solutions of these equations, at least not in a non-perturbative sense. But if you go to the high temperature limit, so it's inverse temperature to 0, these equations all become algebraic. So they become some coupled recurrence equations, which means that one can solve them analytically. And what is remarkable then in this limit, so if you consider the grand canonical equilibrium state, all that is left are just dependence on the chemical potentials, which are denoted by H. That couple to different Cartan charges. And then the solutions to these equations can be expressed in a very compact algebraic form, which is known as the Y system. This, I believe, goes back to Zamolodchikov. So in the unitary cases, the Y system are some nonlinear equations, some recurrence relations, in fact, of this form. And they admit solutions in terms of classical characters. So chi is a character of a representation that corresponds to a rectangular Young tableau with A rows and S columns. And so if you know what these characters are, there will be a function of all the chemical potential of the Cartan charges. You take the certain ratios of these characters, you obtain this Y function, and then by iterating this equation, you have all the Y functions. And if you have the Y functions, as I showed you before, then you know what are the Fermi occupation functions of these modes. Okay, in simple terms, this means that in the infinite temperature limit, we can completely describe thermal states by only knowing information about characters of classical representations. And this is important because it turns out that for what follows that to find out what are the transport properties of these models, it is sufficient to deduce what are the properties of these quasi-particles that carry large quantum number S, so large amount of charge, if you want. And this information is not modified by changing temperature or other chemical potential of the state. It's only modified if you're changing the chemical potential decoupled to the Cartan charges. So it means that having at disposal this information that is contained in the classical characters is basically all that we need, and that's supplemented with information that we have from the nested beta equations, which also know about the underlying root system. It means that ultimately everything that follows is fully dictated by the underlying algebra. Okay, I think I will skip over some parts because this might be too technical. So let's now finally talk about transport. So now we'd like to compute transport coefficients, in particular those transport coefficients that pertain to the transport of the Noether charges, so those charges that are induced by the non-abelian global symmetry of the model. So we are now in the setting of the Kubo's linear response theory. So we have a number of charges with density Q. They satisfy the local continuity equation. We introduce the conductivity, which is the coefficient that tells us how the gradient of the potential, or what current does it induce. In general, this is a frequency-dependent object, right? And it consists of two parts. So one is the delta singularity at zero frequency, which has a weight calligraphic d. This is known as the Drude weight. And then the rest is the regular part of the optical conductivity. So since we are dealing with integrable systems, the Drude weight will be non-zero in general, which signals that the fact that due to many conservation laws in the system, the currents cannot fully decay. So there will be some ballistic transport at large times in the system. And the other part, the regular part of this conductivity is a more difficult to obtain, but it turns out that if we are only interested in the zero frequency limit, so the so-called DC conductivity, then this is the object that hydrodynamics can capture. Okay. So now to quantify the transport, alternatively, one can also use the Kubo formula, which is based on the integrated current correlation function. But we will not use this formula. We will rather use the formula at the bottom, which basically tells you that you just compute the variance of the dynamical structure factor and see how it spreads at large time. So if the dynamics was just normal diffusion, it means that we go proportionally to time, and the proportionality constant is the diffusion constant. But it may happen in certain cases that it goes faster than linearly. And in this case, one can introduce dynamical exponent alpha through this asymptotic scaling of the variance. And this is also related to the dynamical exponent z, which is just 1 over alpha. This is a more conventional choice. Okay, so now what we'd like to understand, we would like to deduce this dynamical exponent z for the transport of the Noether charges in integrable models with non-abelian symmetry. That's the task at hand. So I should point out that the framework of the generalized hydrodynamics allows you to derive exact and compact formula to express both the Drude weights and the DC conductivity of the model. So just to give you an idea, so the Drude weights for different charges can be obtained simply summing over the quasi-particle spectrum. So this is the sum over all quasi-particle species A, integrating over all the rapidities. So then under the integral, one has the densities of this quasi-particle. There is the Fermi occupation functions, which knows about the underlying equilibrium state. There is the square of the effective velocities that these quasi-particles have due to dressing, and they are the dress charges. So it's a simple formula like this. Now, if you take in a generic conserved charge in the model, then this Drude weight will be some positive number. But it turns out that the Noether charges are exceptional in this regard. And this is because in certain cases, in particular in equilibrium states that are not magnetized or not polarized, it happens that there is a perfect screening among among these quasi-particles, and then as a result, the dress charges that they carry will vanish. So Roman already was talking about that a little bit when he was giving this picture of the domain walls that are passing through one another in the spin chain of the Heisenberg spin chain, and because we are then at large timescales, effectively this domain wall passing through other domain wall will be stripped of its magnetization. So that's kind of a similar mechanism, is far more general, and occurs in other spin chains as well, which possess this non-abelian symmetry. So it means that the Drude weights will be zero. And then generically, one would expect that there will be some non-zero DC conductivity or equivalently non-zero diffusion constant, which also assume a very compact exact expression, how it can be computed. But it turns out that if you plug all this data that you obtain from the nested Bethe ansatz into this formula and sum over all the quasi-particle spectrum, you will find out that this DC conductivity is divergent half filling. So the situation is the Drude weight is exactly zero and all the DC conductivities diverge. So we need to have superdiffusion. That's an analytic proof that there is superdiffusion in the system. So now the question is how to quantify what type of superdiffusion, and in particular to infer the dynamical exponents that quantifies it. So here the idea will be presenting very briefly, basically, it's just a refinement of the earlier idea by Roman Vasseur and Sarangopalakrishnan, where they use a scaling analysis within the kinetic theory framework in the Heisenberg model to establish that the exponent there is 3/2. So now the question is, can we do this in more general terms? So the idea here is always to find some way of regulating this diffusion constant, in a sense to render it finite manifestly. And this can be done simply by imposing by hand a cutoff in the spectrum. So we can start summing over all the quasi-particle species, but then we stop at some quantum number S star, which means we just neglect very, very large bound states, for example. So then the diffusion constant D will be finite. And then we can ask upon removing this cutoff, how does this diffusion constant blow up? And let's say that we assign some exponent epsilon to how it blows up as a function of this cutoff, when the cutoff is sent to infinity. So, and on the other hand, we can ask, so this is how does this diffusion constant blow up in this, if you want, in the space of, in the spectral space, but you can also ask in the time domain how this happens. And then again, as a function of time, the time-dependent diffusion constant has to grow. Assuming that it grows algebraically, we can assign to it the exponent alpha that I introduced earlier. And finally, another exponent that is useful is to quantify how do effective velocities of quasi-particles as a function of S, so when they are becoming larger and larger, drop off. And this will be quantified by an algebraic exponent, nu. And then with a simple, essentially simple scaling analysis, self-consistent scaling analysis, you can relate these different exponents. And so yeah, so basically what you do, you just introduce a length scale, which basically divides the spectrum of quasi-particles into two pieces. The light spectrum is the spectrum of quasi-particles which until time t already dress themselves, and then there is a spectrum of heavy quasi-particles which until time t do not yet have enough time to dress themselves, so they will be still free. Okay, so there is some competition of scales, and then when you finally take time to infinity or remove the cutoff, by taking all these scales, you can see how, in what manner the diffusion constant blows up, and you can express this in terms of these two exponents, nu and epsilon. And the outcome of that analysis is that the dynamical exponent Z has to be given by the following fraction. So just to check that this is all good, one can then take the input of the Heisenberg isotropic SU2 chain, where both nu and epsilon are 1 in that case, plug it into the formula, and you indeed find it is equal to 3/2. So now at this point, one may get super excited because if you recall what Romain told you is that, well, the key role of integrability in this story is essentially to render lifetimes of quasi-particle excitations infinite, so to stabilize these quasi-particles, and the rest is pretty much just the kinetic theory, as I flashed on this slide. So one may, jump ahead here and say, well, let's not care too much about what is happening under the hood. Let's just assume that we have quasi-particles with particular properties. So let's just impose by hand that there are quasi-particles where the exponent u is such and such, and the diffusion constant blows with epsilon, which is such and such. So let's just make up these numbers, and then it means that we will have a whole range, infinite tower of dynamical exponents as given by this fraction. Now that will be like one could propose this thing, but who tells us that such a choice is consistent with more fundamental microscopic principles? That's the question. And what I want to convince you now quickly is that indeed this is not possible, because there are further constraints that need to be respected. Okay. So first of all, these two exponents nu and epsilon, as I introduced them, cannot be independent, and this is simply because the way the diffusion constant blows up in the spectral space is controlled by the effective velocity of quasi-particles, which are basically determined by this exponent nu. So these two objects are linked. And the other thing also, which we completely disregarded, is that if you have an integrable system with a Nonabelian Lie group symmetry, this exponent nu, which tells how the effective velocities drop off at large quantum number s, it cannot be arbitrary. Okay, so what happens is that by finding another scheme to regulate the diffusion constant, namely by switching slightly all the chemical potential to a small value, everything will be regulated, and then we can again expect how this things scale upon again switching them off, this chemical potential. We find another relation between these two exponents, which is that their sum must be equal to 2. Okay, so now these two, combining these two laws and using that, if you have the nested Bethe-Ansatz equation underneath, which derive from the Youngian symmetry of the model, the exponent nu must be an integer. This means that there are only 3 options that you have, which are listed here. So one option would be that nu equals 0, but this would imply non-vanishing Drude weights, which can be a priori excluded, as I showed you.